Hope you're enjoying the test. We're going to enter a little bit more of a challenging section with proof by contradiction, specifically with rational numbers and integers. We have an example here. I'm just going to do 3 examples, but first example is to prove the following. If a, b, c are odd integers, then a quadratic of ax squared plus bx plus c equals 0 has no solutions in the set of rational numbers. This is kind of a neat little feature of trying to set up problems for quadratics. We'll never come up with rational solutions if a, b, and c are all odd integers. That's, again, I think it's interesting. A curiosity, but still interesting. So, when you prove by contradiction, one of the things you're doing is you're trying to set up the conditions of the problem in such a way that you're defining your instances. So, when we start with a proof by contradiction, we assume the opposite is true. Now, a proof by contradiction can be identified as a possibility whenever you have mutually exclusive cases where they're either ax squared plus bx plus c has no solutions, or it has at least one solution. So if we assume the opposite is true, we assume that there is a solution. Assume the opposite is true, and we're going to say suppose there is an x that is a rational number. So to make x a rational number, we have to make it p divided by q, where p and q are both elements of the integers. This just means that they're both integers. And we can also assume, without loss of anything, that p over q is in lowest terms, or that it is a simplified fraction. Another way to say this is that p and q are relatively prime. This is actually more of a proper way to say it. We never talk about lowest terms in high math. We say relatively prime, which specifically means that there is no common prime factor. In fact, I'm going to cheat and use this as sort of a definition for relatively prime, so I can use that for future proofs. So if we do a substitution, we're going to get a times p over q squared plus b times p over q plus c is equal to 0. And if I multiply both sides by a q squared and simplify, I'm going to get ap squared plus bpq plus cq squared is equal to 0. And from here, we can start to pull apart and identify our specific cases, our specific possibilities for how this is going to play out. And we're going to do this by analyzing p and q, seeing if that they're both odd or both even, or one's even and one's odd. If p and q are both even, then they're not in lowest terms, or they're not relatively prime. So that can't be true. So p and q can't actually both be even. Well, that's kind of obvious. So let's kind of go with p and q both odd. Well, if p and q are both odd, then an odd squared times another number, and again, we have an odd squared times an odd. So this is where we're using the fact that the original one is odd. ap squared is 3 odd numbers times each other, so I know ap squared is odd, plus bpq is an odd times an odd times an odd, and that's odd, plus cq squared, and that's an odd number, again 3 odds, and an odd plus an odd plus an odd equals 0. We basically have an odd number is equal to 0. Basically an odd equals an even. So that's not true. And I'm going to say sum is odd. Just kind of off to the side, I just want to write down 0 is considered even. That should be obvious, but for some it's not. Okay, let's expand this out. And then finally we have the case of where if p is odd and Q is even. And realize that I could swap those out and make Q odd and P even without changing anything. So I'm going to put or vice versa. I want you to take a moment and convince yourself of why you could swap those out. Essentially it has to do with the symmetry of the quadratic equation up here. Oops. That, just try to erase this circle here. The symmetry that you just kind of have the same thing going on with P and Q. So if P is odd and Q is even, or vice versa, what you end up with is, we know that AP squared is going to be odd. We know that BPQ is going to be an odd times an even times an odd, so that's an even. And then I know that CQ squared, Q is even, and even squared is an even, and an even times an odd is an even. So this is going to be plus an even. So I have an odd plus an even equaling 0, or an odd equals 0. And so once again, the sum is odd. At that point, that's enough to do the symbol we showed earlier, the triangle with the arrow in it, saying contradiction. I have either a case here that contradicts something earlier, not relatively prime, or my sums are going to be odd no matter what. In fact, the only way for the sum to be even is if P and Q are both even, and that can't happen. So that's enough to say contradiction. And once we do a contradiction, that can be the end of the proof. I just want you to realize this can be, if you want to write one more thing, you can say therefore, well, you know what, we're not going to write that. Let's just kind of leave the contradiction symbol and keep it with regular math. Therefore, we know that the proof is true, or the proof is valid, that there are no solutions, because there can't be at least one. Second example. X squared minus y squared equals 1 has no positive integer solutions. This is just another way of saying that the difference of squares cannot be 1. We can try to look at induction with that one if you want to. I don't think it can be proved really with induction, since we're incrementing by integers, yes, but we're not, you've got two things going on there with x and y. So let's try with contradiction. We're going to assume x and y are positive integers. By the way, the reason we have to say positive integers is if we count 0 as an integer, then there is a solution. But x and y are positive integers, and if I factor that, I get x minus y times x plus y equals 1. So the two possibilities that occur from this, because x and y are integers, are either x minus y times x plus, either x minus y equals 1 and x plus y equals 1, or x minus y equals negative 1 and x plus y equals negative 1. Basically, they either both have to be 1 or they both have to be negative 1. So if I continue with the first one, if x minus y equals 1 and x plus y equals 1, if I take them and I solve them, as a system of equations, let's just add the left and add the right. X minus y equals 1, x plus y equals 1, 2x is equal to 2, and x is equal to 1. X is equal to 1, which makes y equal to 0. Well, that won't work because x and y are both positive integers. Let's kind of look at the other side. X minus y equals negative 1, x plus y equals negative 1. Add them. 2x is equal to negative 2, x is equal to negative 1, and y is equal to 0. Well, that's a double contradiction because neither of them are positive integers. So since we have two cases in either or, and neither of those can be true, then we can say contradiction. The last one is a classic proof that you really should be exposed to, and you can whip out at cocktail math parties if you're up for it. The proof that radical 2 is irrational. This is in many, many algebra books, including our own. So what we have to do is we have to say, if we're going to prove that radical 2 is irrational, Right. And we're going to do this with a contradiction. Let's assume that radical 2 equals p over q, where p and q, and you guessed it, are relatively prime. And the classic way we go with this is we square both sides, so 2 is equal to p squared over q squared, and then maneuver that into p squared is equal to 2q squared. And then we look like a little back and forth. This is one of my favorite things. Because p squared is equal to 2q squared, this means that p squared is even. Since p squared is equal to 2 times something, so since p squared is even, this means that p is even. Here's the back and forth part. Because p is even, this means that p is equal to 2 times a, for some integer a. And if I do a substitution way right here, I get 2a squared is equal to 2q squared, or 4a squared is equal to 2q squared, or 2a squared is equal to q squared. And then by the same logic that we used up above, q is even. So all this comes from the fact that we can just clearly say that p is even and q is even. We can do this by just a simple analysis. If p is even is q and even, then p and q are not relatively prime. Oops. And that's the point where that contradicts one of our things up here. So, contradiction, and we know that radical 2 is irrational. So, that's it. Your homework's a worksheet, and see ya.